Alright, so today's lesson number 2 for our energy unit. We're going to start with gravitational potential energy for the first half of the lesson, do some examples, and then we're going to move and go over the concept of conservation of energy. So gravitational potential energy is a stored energy due to an object's position in a gravitational field. So what this means is if I were to take something, a tennis ball, and lift it up in a gravitational field some distance, then it has stored energy. And you can see that energy exists when I drop it because it gets converted to kinetic energy as it falls. So how much stored energy does it have? Well, here's our equation that we're going to use. So gravitational potential energy is the object's mass times the gravitational field strength that it's in times the height that you raise it to. Now there's a change there, right? And that's important because you can calculate change in gravitational potential if you lift something from this high to this high. And it also is important where you measure height from. It's also an arbitrary choice, as we are going to see in some examples. So let's try the first example. So the first example says here we have a drop tower gondola, so like at an amusement park, a drop tower, like Tower of Terror or Drop Zone, something like that. And its passengers have a combined mass of 500 kilograms. So the whole thing is 500 kilograms. What's the change in their gravitational potential when they're lifted 48 meters up from the base of the tower? All right, so here's base of the tower. So here's the base of our tower. And let's say the tower is this high, okay, and it's raised to some height of 48 meters from the base. We can calculate that change in potential energy. So basically the base is where we're going to have the height be 0. And then the height at the top will be 48. So our change in gravitational potential energy is just equal to mass times the gravitational field strength we're in times our change in height. So our mass is 500 kilograms. And our G value is 9.8. We'll use 9.81 newtons per kilogram. And then our change in height, it's always final minus initial, so it's 48 minus 0, which is just 48. Okay, so that's going to equal, so 500 times 9.81 times 48. All right, you have 235,440. So I'm going to round this off to 3 significant digits and put it in scientific notation. So 2.35 times 10 to the power of 5. And the units, just like work and kinetic energies, gravitational potential energy is energy, so the units are joules. All right, so the second question shows the importance of where we can choose the height to be 0. It doesn't always have to be the ground. For example, previously I took this tennis ball and I dropped it, so it hit my desk. Well, I measured the height from my desk, not from the ground, certainly not from sea level, right? You can choose where h equals 0. And your choice will depend on the problem you're given. So let's look at this example. This example here, we have a lake freighter with a total mass of 35,000 megagrams, so 35,000 tons. Travels from Lake Huron, which is 176 meters above sea level, to Lake Superior, which is 183 meters above sea level, through the Soo Locks. So find the change in the freighter's gravitational potential energy using sea level as a reference. What does that mean? It means we're going to make sea level where h equals 0. So let's imagine we have sea level down here, and then we have Lake Huron here, and Lake Superior here. So this would be a height of 0. This would be a height of 176. And this would be a height of 183. All right, and we want to know the change in gravitational potential energy if our boat goes from here to here. All right, so we can calculate that. Change in gravitational potential energy equals mass times g, which is 9.8, times our change in height. Okay, so our mass is 35,000 megagrams, or 35,000. We'll change up megagrams into kilograms, so let's multiply that by another 1,000, or 10 to the power of 3, because we want it in base units, which is kilograms. G is going to be, so that I should write kilograms. G is going to be 9.81 newtons per kilogram. And of course our change in height is final minus initial. So our final height is 183 from sea level meters, and our initial height is 176. Okay. Now what this gives us, and I want to look at this specifically, so 183 minus 176 gives us 7 meters. So if we want to know the answer, it's going to be huge because the mass is so big. Times 9.81 times 7. Wow, big number. Let's use scientific notation here. So 2.40 times 10 to the 9 joules. Okay, so what's important is where we chose H. Now part B says to choose Lake Huron as our reference level. So let me change the color here. So what does that mean? It means Lake Huron, we're going to say, has a height of 0. And then Lake Superior then, which is 7 meters above Lake Huron, would have a height of 7 meters. Because we're referencing it from how high is it from Lake Huron. It's 7 meters above Lake Huron. Now if we choose that to be our height of 0, and we were to solve the same problem, to figure out the change in gravitational energy, well, that's going to be mass times gravity times our change in height. Now mass and gravity are still going to be 35,000 megagrams, and gravity is still going to be 9.8. So let me just write mg. But our change in height is going to be final minus initial, which is 7 minus 0. And notice that that gives us 7 meters. It's no different from what we got over here. This change in height is 7 meters. This change in height is 7 meters. So it doesn't matter where you choose h to be 0. Now obviously, this h made a lot more sense. I mean, like when I take my tennis ball here and I drop it, I could measure the height of my desk from sea level, and I could measure the height of the tennis ball from sea level and calculate it that way, but why would I do that? I can just measure the height from my desk and say the desk has a height of 0. Makes things a lot more easier if we can do this. Okay, and therefore we're going to get the exact same answer of 2.4 times 10 to the 9 joules. Okay, so the next two terms I want to talk about is 1, total mechanical energy, and conservation of energy. Total mechanical energy is simply you look at a system and you add all possible kinetic energies with all possible potential energies. And you get your total mechanical energy, all the energies in that system. Now, conservation of energy says that that total mechanical energy in a closed system remains constant, meaning energy cannot be created nor destroyed. It simply can get transformed from one form of energy to another form of energy. So what do I mean by that? Let's say I'm right here and I plug in a stereo. That stereo takes electrical energy. Then it converts it into kinetic energy because the speaker starts vibrating. Those vibrations convert into sound energy that travel as a wave through the room that you then hear. Okay, there'll be some energy because it's a mechanical system. Usually always get some energy turned into heat, especially when you have moving parts. There's always frictional forces there, and friction creates heat. But if you were to add up all of these energies, nothing is created or destroyed. It remains constant. Now, another important thing there is I said it remains constant for a closed system. What do I mean by that? Similar to how we choose where h equals 0, we choose what our system is. So let's look at this example. Here we have two people in a room. They're exchanging money. They can exchange money back and forth as much as they want, but the total money between them isn't going to change. Then someone here opens the door and hands in more money. Well, now the amount of money in the room has increased. We've learned about this before. We call it work. Right? If you apply a force on the system, depending on whether it's positive work or negative work, you can give or take away energy from that system. So that's what this person is doing right here. He's adding energy or adding money to the room. But that depends on what your closed system is. If you considered the room to be a closed system, then yes, energy or money was not conserved because more came into the room from outside of our system. And so it's not a closed system anymore. However, if you considered that whole building to be your system, well, this other person's been in the building the whole time, so you would have counted that person's money from the beginning. And therefore, the money in that building, in that closed system, hasn't changed. It's conserved. But again, then you can have people coming from outside of the building, right? As long as you have no external force acting on that system, which we call work, then total energy of that system is conserved. So let's look at an example that's not money in a room. Let's look at a physics example. Let's say I take this ball and I throw it up. It goes up and it comes down. So we have it initially, after it leaves my hand, it has a certain kinetic energy. But it's losing kinetic energy as it goes up, and it's becoming potential energy till it reaches its maximum height, and it has no kinetic energy at all. And then it starts coming down, and all that potential energy gets transformed back into kinetic energy. So let's pretend that our system here, I'll label my system, is the ball. So we have a ball. Okay, so what's happening then? Well, we have our ball, and initially it has some sort of kinetic energy. Kinetic So initially the ball has some kinetic energy, and then as it moves up in its path, suddenly it doesn't have any kinetic energy anymore. Well, where did it go? Well, what happened to it was there was an external force acting on the ball, and that external force was the Earth, providing some force of gravity on it. And so the total energy in that system is changing because gravity, or the Earth, is doing work on the ball. But what if we assumed the ball and the Earth is our system? It's the whole thing, the ball and the Earth. Okay, so here we have the Earth. We throw the ball. Initially, it has, again, kinetic energy. And as it goes up, it now has potential energy due to the gravitational field of the Earth that it's in, which is now part of our system. So all the kinetic energy is gone, but it now has gravitational potential energy. Are these two situations different? No. Let's look at it mathematically. I'm going to change colors here so we can look at it mathematically. So the first example, what do we have? Well, we have work being done by gravity, and we have kinetic energy. So let's say we start with kinetic energy, and then we have work being done by gravity, so plus the work being done by gravity. And that ends up being, up here, all of our energy going away to zero. Okay, well, what about over here? Here, we have all of our kinetic energy, and that ends up having gravitational potential energy. So the question is, are these two equations the same thing? Well, let's look. Kinetic energy is 1/2 mv squared. Now the work done by gravity is actually negative work because its displacement is up and the force is down. So it's minus the force of gravity, which is mg, right? Fg is mg, if you remember that from our forces unit, times the distance it traveled. But the distance it traveled is the same as its height, h, which equals 0. And if you want, you can rearrange that and you can write 1/2 mv squared equals mgh. That's what this is. Gravitational energy equals kinetic energy. 1/2 mv squared equals mgh. So it doesn't matter from what point of view you look at it from or what you choose your system. Kind of like when we did gravitational potential energy 10 minutes ago. I said it doesn't matter where you choose h to be. In this case, it doesn't matter what you choose to be inside of your closed system. You just need to make sure you account for everything in your system and if there's any work being done on your system. So we'll try a problem now with conservation of energy. And the hard thing students find with conservation of energy problems is really I've only told you two equations. I've taught you, other than work, I've taught you the equation for kinetic energy, and I've taught you the equation for gravitational potential energy. What you have to do for every energy problem is set up the problem yourself. So what do I mean by that? Let's try this example. This example says we have a toy car up here. It's set up on a tabletop. The mass of the car is 25 grams. We'll have to change that to kilograms. Calculate the speed of the car at the bottom of the ramp, so down here. So up here, it's not moving, but because of its position, it has gravitational potential energy. Down here, it is moving, so it has kinetic energy, and due to its position, it could have gravitational potential. It just depends. It just depends on whether or not you want to make the floor your height of 0, or if you want to make the tabletop the height of 0. Again, it doesn't matter which one we do. I am going to make the tabletop the height of 0, because like I said earlier, if I'm dropping the tennis ball onto my table, I may as well make the table a height of 0. So, if the tabletop has a height of 0, then the top of this ramp, you can figure out its height by finding the difference between 2.15 meters and 0.95 meters. So subtract those two, and you get 2.15 minus 0.95, you get 1.2. So 1.2 meters. It's pretty high track. Alright, so how are we going to figure out its speed at the bottom? We have to apply conservation of energy. And conservation of energy just looks like this. Total energy is constant. So I can write total energy equals total energy. But that seems like a useless equation. One thing equals another. What we have to do is label different points. So let's call the point up here A. That'll be point A where the car is up top. So I can say the total energy at A equals, and I can use this as point B, equals total energy at B. Now this equation can actually do something for us. Now the total energy at A, we have to think, what are all the possible potential and kinetic energies at A? Well, it's not moving at A, so there's no kinetic energy. But it is lifted up from the table, so it has gravitational potential energy. So at A, we have gravitational potential energy. E G. I'm having trouble with my pen today. Alright, what about at B? Again, at B is definitely moving. So we have kinetic energy at B, EK, at B. Alright, what about gravitational potential? In the problem that I set up, it doesn't have gravitational potential because I chose the height of the table to equal 0. If you chose the height of the floor to equal 0, then it would. But don't worry, as you saw in the previous problem, you'd still get the exact same answer. I'm just making the problem a little bit easier for me. This way, I only have 2 terms instead of 3. Alright, so the gravitational energy at A is mgh. This would be the height at A. If you want to specify, you can specify the height at A so you don't confuse yourself later. And that's going to equal the kinetic energy at B, and we could specify that too, which would be 1/2 m times the speed, again if you want to specify, at B squared. It's good to always do subscripts A and B, just in case if the car did start with an initial velocity at A, we'd have kinetic energy here. You just don't want to have a V here and a V here and think they're the same V. They wouldn't be. Alright, so now all we have to do is solve for that V, right? Because that's what the question is asking for if we forgot. Calculate the speed of the car at the bottom of the ramp. Now it turns out we don't actually have to convert 25 grams into kilograms because we have a mass terms on both sides of the equation. It cancels. So rearranging for VB, okay, we just multiply by 2 and take the square root. We get the square root of 2 times G times the height at A. Right? We can put in all of our numbers now. Which is 2 times G, which is 9.81. Newtons per kilogram. Times by the height, which we have is 1.2 meters. And we get our speed B. So the square root of 2 times 9.81 times 1.2 is 4.85. But rounding the 2 significant digits, 4.9 meters per